In all of our sections so far for Unit 5, we have been discussing, and we kind of touched on the collision model a little bit, but in 5.5 we're going to discuss it further. So the collision model is built around the central idea that molecules must collide to react. There are many factors that can increase the rate of reaction based on the collision model that we saw in 5.1, but experimentally it's been found that the rate of reaction is much smaller than the calculated collision frequency. So this means that only a small fraction of collisions actually produce a reaction. Why is that? Well, we kind of discussed it a little bit in 5.1, but for any elementary reaction to successfully produce products, that's a typo, sorry, reactants must successfully collide to initiate bond breaking and bond making events. So that minimum energy that they need, because they have to have enough energy and they have to be oriented properly, those are the two things from 5.1, remember. That energy is called activation energy. This is a barrier that the reactants must cross before the products can form. So do you know that the activation energy is this height right here on the graph, where reactants are what you start with and then products are what you end with. So as the reaction takes place, the hump is how much energy is required, and that is from the height of energy for the reactants value and the height up to the peak of the graph. Now every particle in the reaction has sufficient energy, only a small fraction do. When two reactants will collide and they can start to react, they form what's called an activated complex. So we say that the activated complex is located at the top of the activation energy barrier. When they have collided and they are together momentarily, they are also known to be set into transition state. So it's something that we don't ever see, but it is when all of the molecules have kind of stuck together and they're rearranging on themselves to break apart into the new products. So again, the activated complex is at the top of the activation energy part of the graph. In 3.5, we first discussed Maxwell-Boltzmann distribution curves, which, remember, the curve, if speed is on the x-axis, the number of molecules, the total area under the curve is all of the molecules that are present in the reaction. And then based on its speed, we have the average speed point on the graph and the most probable speed, and then the root mean square speed. And remember too that we saw this in 3.5, that temperature has an effect on the speed of the molecules. So when it's very cold, the speed will be lower, and when it's very warm, the speed will be higher. But the way that the graph moves is so that the number of molecules under the curve stays the same, or that the area under the curve stays the same. Well, how does this relate to activation energy? These curves can give us a qualitative estimate of the fraction of collisions with sufficient energy to lead to reaction, and also how that fraction depends on temperature. So instead of putting speed on the x-axis, we could put kinetic energy, because those are related. And so at some point on that x-axis is the minimum energy needed for the reaction, or the activation energy. So if you know how much energy is needed, and you can study some experiments at different temperatures, you can see that at a higher temperature, more molecules are past the activation energy line, and so that means that more of the reaction can take place. But that also explains why not all of the reaction is taking place every time they collide, because they haven't passed that activation energy barrier. So as the temperature increases, so does the probability of molecules having higher energy, so then the probability that they're actually going to react is higher as well. So again, and to conclude, we know that things have to collide in order to react, but not everything does react. And from data, from experiments, we found that we have to have enough energy to do so. And so even though things collide all the time, they might not react. And it all has to do with passing over that activation energy barrier.